Welcome back, everybody. Today we are going to start the Chapter 10 lecture note outline, and this is the last chapter of Unit 3. So in Chapter 10, we're going to be learning about gases, and we're going to start by learning about the laws of gases. And when I say laws of gases, what I mean is we are going to learn how to predict what will happen to a gas under different circumstances. So circumstances like what happens to a gas volume when the pressure is increased or decreased? What happens to the pressure or the volume when the temperature is changed? So we're going to learn how to predict all of the different phenomena that gases exhibit when they're subjected to various types of changes, and we're going to develop some simple mathematical concepts to do that. Now, the first thing we have to learn about when we're talking about the gas phase as distinct from the solid and the liquid phase is the concept of pressure. Now, to understand pressure, let's go back to our concept of solids, liquids, and gases and compare each of these phases of matter or states of matter. We know, for example, that a solid has a definite shape and a definite volume. So when we have a solid in a container, there's no interaction of the solid with the walls of the container that it's not in contact with. So changing the volume of this container has no effect on the properties of this solid simply because it's not in contact with it. That's a similar issue with liquids, right? Liquid only has a contact with the area of the container that it's directly in contact with. It doesn't have any influence over this part of the container. So if I change the volume of this container that it's in, there's no effect on the liquid. Now a gas, however, it has a different situation because it doesn't have a definite shape nor a definite volume. In fact, it not only takes the shape of the container it's in, it will also take on the volume of the container that it is in. And this happens because the particles that comprise the gas are not localized to one specific area within the container. They are freely moving, freely mobile from one another. And for that reason, they collide with the walls of the container, as I'm showing here. Each time one of the particles that comprise that gas that is in the container collides with one of the walls of the container, it exerts a force on that container. And this force is called pressure. Now, it follows from this that the pressure and volume of a gas will be in some sense dependent on one another. This is due to the fact that a gas takes up the entire volume of the container that it is in. So we will see that changes in the volume of a container that a gas is in will have a direct impact on the pressure of that gas. And conversely, the pressure of a gas can have an effect on the volume of a container if that volume can change. So let's keep this in mind as we continue to learn more about gases, and remember that all gases, even those that we cannot see, exert forces upon the objects or containers that they are in contact with, and for that reason, they have a pressure. Now here I have an example below called a Torricelli barometer. And a Torricelli barometer is a device that is used to measure a gas that is all around us, yet we can't see, that of the atmosphere, or the air in the atmosphere. Now, a Torricelli barometer is essentially made up of a tube, a glass column like this, that is completely filled with mercury. And that tube is then suspended inside of a container that contains another pool of mercury. So it's suspended upside down like so. And when it's suspended, the mercury, of course, starts to drop. It starts to gradually fall down the tube, but then it eventually stops, and we are left with a space up here at the top of the column of mercury. Now, if you measure the height of this column of mercury and write it down, you will notice that it changes depending on the time of year, even the time of day, or the location around the Earth. Here are some examples. So as you can see in this table, I have several locations from around the world, including Death Valley, Paris, France, here Coeur d'Alene, Idaho, and Mount Everest in Nepal. I also have listed the altitudes of each of those locations, the approximate altitude in feet. And then finally, in this column that I'm going to fill out here, I have the atmospheric pressure, or the reading from a Torricellian barometer listed in millimeters of mercury. Most weather sources here in the United States provide these readings in inches of mercury, but in chemistry we typically use millimeters of mercury. So here are the readings I pulled off the internet from yesterday. Death Valley, California was listed as 655 millimeters of mercury. Paris, France, we had a little bit lower at 759 millimeters of mercury. Here in Coeur d'Alene, Idaho, it varies quite a bit, especially recently, but I read off our barometer here in the lab at 748 millimeters of mercury. And then I found a reading in Mount Everest. These aren't recorded on a daily basis, but I found a historical one that was listed as 250 millimeters of mercury. So what trend do you notice on this table as we change altitude? What happens to this millimeters of mercury reading as we go up in altitude? So notice that we start here in Death Valley at this really low altitude. That's below sea level. So if we start, let's imagine that the column of mercury is up here at 765 millimeters of mercury. And then we go to Paris, France, right, where that's way up in altitude. That's at 115 feet above sea level. What happens to the millimeters of mercury? Does it go up or down? That's right, it goes down. So as we increase in altitude to Paris, France, the column goes down. It drops down a bit to here, let's say. And then we go to Coeur d'Alene, Idaho. And again, we're going up about 2,000 feet. And what happens then? The millimeters of mercury drops down. And then we go to Mount Everest, and we see it goes down to like 250 millimeters of mercury. That's like way down here, let's say. So what happens is, as we go up in altitude, the column of mercury drops down. So why is that? What's going on? What is making that column stay up, and what is changing its height? Well, it turns out it's the pressure of the air, the gas molecules in the air that are in the atmosphere all around it. And they're impacting with the surface of this pool of mercury, literally colliding with that mercury pool. And when they make those collisions, they're actually exerting a force on that pool of mercury, causing that column to stay suspended rather than falling out and spilling out the outside of the pool. So if there's more atmosphere here, there are more collisions on that pool of mercury, and therefore the column gets higher. So that's down in Death Valley, I should say, way down below sea level. There's a lot of atmosphere above that pool of mercury pushing down on it, causing the column to rise. So, and then if we take atmosphere away, like on Mount Everest, there's less atmosphere, and therefore the column drops down. So that's what a Torricelli barometer is, and that's what causes the change in the height of mercury. And that's also what we use to measure barometric pressure, or atmospheric pressure. And this brings us also to the typical units that we use in chemistry to discuss pressure of gases. We frequently use units that are directly measurable by Torricelli type barometers. So we use something called millimeters of mercury, which I showed you here. And we also use the atmosphere unit, or 1 atmosphere. 1 atmosphere, or an ATM unit, is the pressure that you would read on a Torricelli barometer at sea level, which ideally is 760 millimeters of mercury. So the unit atmosphere, or 1 atmosphere, is equal to 760 millimeters of mercury. We also use a unit called the Torricelli on occasion. The Torricelli, of course, is related to the Torricelli barometer, and there's a unit of torr, which is another unit for pressure. 1 torr is equal to 1 millimeter of mercury. So 1 atmosphere is equal to 760 torr. So now we're going to go to the next page and start our discussions of the different laws which govern gases. The first gas law that we will study is called Boyle's law. Boyle's law is a law which expresses the relationship between the volume and the pressure of a gas. So it seeks to explain how the volume of a gas would change if the pressure is changed, or if the pressure is changed, how would the volume change? This is called Boyle's law. So gases, unlike solids and liquids, are compressible. That means they can be confined to small volumes or allowed to expand into larger volumes. But how do we compress a gas into a smaller volume? Well, we have to use pressure. So in the diagram I have here, we see a gas confined to a container with a volume that we can move up and down with this piston. So there's a piston here that can be moved up or down. And if the piston is moved down, the volume of the gas decreases. If the piston is moved up, the volume of the gas increases. So we see that going from left to right, the volume is decreasing. Now, what is happening to the pressure as the volume is decreasing? Well, the pressure is increasing, right? In order for that volume to decrease, we have to apply a force to the top of each of these pistons. That's represented by the masses that are shown on top of each of the pistons increasing. Increasing that mass increases the force on the gas, and therefore the volume decreases. So the volume decreases as the pressure increases. It turns out this is the basis of Boyle's law, so let's summarize these observations. As the pressure on a gas increases, the volume decreases, and as the pressure on a gas decreases, the volume increases. This is an inverse relationship, or an inverse proportionality. What I mean by that is, as one goes up, the other variable goes down, or vice versa. So it turns out, just from these simple observations, we can write down the mathematical form for Boyle's law. And we start by using the symbols V for volume and P for pressure. Now we see that volume and pressure are inversely proportional to one another, so let's write that down in symbolic form. Remember that to show a proportionality, we can use the proportionality symbol. And if we want to show the inverse proportionality between volume and pressure, we have V on one side and then the inverse of pressure on the other. This is the inverse relationship, or inverse proportionality, between volume and pressure. Now, someone named Robert Boyle decided to study this, and instead of just settling on a proportionality, he wanted to set out to find some kind of law that he could write an equal sign there instead of a proportionality. Boyle did this by looking at the volume and pressure for various gases and then looking specifically at the data. Now, that sounds really ordinary for what a scientist would do today, but in Robert Boyle's time, which, by the way, was in the 1600s, that was definitely not an ordinary thing to do. In fact, Robert Boyle is largely responsible for the establishment of the scientific method as we use it today. And in fact, Robert Boyle published a book called The Skeptical Chemist, in which he argued that by systematic study of phenomena and the relationships between phenomena, one could establish a science called chemistry. He also argued against the archaic understanding of elements as being only four, being earth, air, fire, and water, and instead argued for a more systematic approach when trying to understand matter and the changes that it undergoes. And while the book is still available even on Amazon, although with the wrong publication date, it's not exactly easy to read, nor is it as relevant as it was back in 1661. What Boyle discovered, though, was that gases and their behavior under pressure are fairly easy to understand, namely that the volume and the pressure are inversely proportional. He also found that there was a constant K, which we'll call the gas proportionality constant, which related the two by inequality. So Boyle found that if you knew the pressure that a gas was under, you could predict its volume, or if you knew the volume, you could predict its pressure. The gas proportionality constant K, which is unique for each gas, made this possible. So it turns out we can still use Boyle's law even if we don't know the gas constant for the gas that we're dealing with. For example, we can rearrange this equation where V is equal to K over P to V times P is equal to K. Now, this form of the equation is useful because it shows us that the product of the volume and the pressure is equal to that gas constant K. So that means the product of any volume and pressure combination that you would observe for a gas would also be equal to that constant K. So for example, I could measure the volume and the pressure at one time and then change the conditions, like the volume and the pressure conditions, and get the new volume and the new pressure, and the product of those volumes and pressures would have to be equal to the same constant K. So the initial condition product and the final condition product are equal to the same constant. So we can rewrite this as the product of volume and pressure at, say, instance 1 and the product of volume and pressure at instance 2 are equal to each other. And this is actually the most useful form of Boyle's law, where V1 times P1 is equal to V2 times P2. This is the form of Boyle's law that we'll most often use. And the way we see it used mostly in this class is when we know 3 of these variables, we find the 4th. So for example, if you knew the initial volume and the initial pressure and the final pressure, you could determine the final volume. Or for instance, if you knew the final volume and the final pressure, as well as the initial volume, you could also find the initial pressure. So if you know 3 of them, you can find the 4th with this equation. So that's the form of Boyle's law that we'll reference later on when we do some problems. Let's go to the next page and look at another gas law, which is called Charles' law. So the next law we're going to look at is called Charles' law. And Charles' law is one of the simplified gas laws that explains the relationship between the volume of a gas and the temperature that the gas is at. So we can see how the volume changes when the temperature is changed. Now, before we get into the details of Charles' law, there's a quick correction I would like you to make. Down here on this graph, we have the temperature unit on the x-axis. The units for that is incorrect. Please change that to degrees Celsius. So like Boyle's law, Charles' law is fairly easy for us to understand. We monitor the volume of a gas as the temperature is either increased or decreased. So you can see an example of that in the diagrams that I have over here. So for example, if a gas is placed inside of a cylinder that has a movable piston that allows the volume of the gas to change by either increasing or decreasing, and there's some way to control the temperature that the gas is at, it's pretty easy for us to measure then the volume that the gas is occupying. And this diagram shows sort of what we would expect, right? If we have a cold gas, the volume is much smaller than if we warm that gas up. So why does this happen? Well, think about this. When we warm the gas up, the kinetic energy of the particles in the gas also increases. And because the kinetic energy increases, that means these are moving much more quickly. So there's an increase in the movement of the particles, and that means there's an increase in the frequency of the collisions occurring at that movable piston. That increases the forces on the piston, and therefore the volume increases. This result is observed experimentally. Once measured, the volume of a gas like nitrogen can be plotted against the temperature at which that volume was measured. Now for the gas nitrogen, as I've shown here, we see a continuous line that sort of implies that all of these data points were actually measured. And in fact, it's not the case. Certain temperature ranges back when this was first discovered were not accessible. So the actual measured volumes were only measured over a very specific range of temperatures that were accessible at the time based on the technology that was available. The other data points that are shown below are extrapolated from that original data set. When this same experiment is conducted on other gases, something very important is observed. When you look at the volume versus temperature data for other gases like hydrogen and oxygen, a trend line can be extrapolated back. And this trend line shows something very interesting. The trend lines, as I've shown here for oxygen and hydrogen, and this is true for all other gases, all converge at the same point. This position, the x-intercept for each of these functions, has some significance. And what is that significance? To understand that significance, let's talk again about what this graph shows, what this data actually shows. It shows that as the temperature of a gas increases, the volume also increases. And as the temperature on a gas decreases, the volume decreases. So what we're saying here is that volume and temperature are directly proportional to one another rather than inversely proportional to one another. If one goes up, the other goes up. If one goes down, the other goes down. Now, what does that say about this position, this x-intercept point that I have drawn here? what volume is predicted, and at what temperature is that volume predicted, and why do all of these gases all seem to go to the same volume temperature convergence? What does that mean? Well, notice that it's the x-intercept. That's when y is equal to 0. And what is y? Well, y is the volume. Well, that's interesting. What we're saying here is what the temperature would be for a gas if the volume were exactly 0. Well, does that make sense? Can the volume of a gas actually be 0? And what temperature would it have to be to actually be 0? So think about this. A gas is comprised of atoms. Is it possible for atoms to have no volume? I don't think so. That's because atoms actually have mass in them. And because they have mass, they must take up some volume, right? Well, probably. But if they could have 0 volume, what temperature would it have to be to get to that volume? Well, that's right. It would have to be very cold. In fact, it would have to be the coldest possible temperature. And this graph predicts what that temperature would be. It predicts what we call absolute zero, or the coldest possible temperature in the universe. And it's actually negative 273 degrees Celsius, or 0 Kelvin. So Charles' law actually represents the first accurate prediction of absolute zero as a temperature. Let's see if we can derive Charles' law from the information we've seen so far. We know that volume and temperature are directly proportional based on this data. So that means we should be able to find some equation where we have V is equal to K times T, and that turns out to be the case. K is this gas-specific constant, and it actually represents the slopes of the lines that we saw above for the different gases. So if the volume is equal to a constant times the temperature, it follows by rearrangement that volume divided by temperature is equal to that same constant. This means that the ratio of the volume to the temperature is always the same. So the volume divided by the temperature at some initial conditions will be equal to the same constant that the volume divided by the temperature at some other conditions will equal. So we can write this out as follows. V1 divided by T1 is equal to V2 divided by T2. And this is the form of Charles' law that we use most often. And we usually use this by knowing 3 out of these 4 variables, and then we can find the 4th. And one quick note before we go to the next page, referring to temperature. When we're using the equations like Charles' law that include temperature in the equation, we need to first make sure that we convert from degrees Celsius. If we're given temperature units in degrees Celsius, we need to convert those first into Kelvin. Degrees Celsius won't work correctly in these equations. We won't get the right results. All right, so let's go to the next page. The law which explains the relationship between temperature and pressure for a gas is called Gay-Lussac's law, and it looks something like this. A vessel with a fixed volume is charged with a gas, and a pressure meter is connected to this gas, so that at any given temperature, a pressure can be read. Now, as before, when the temperature of the gas is increased, so does the kinetic energy increase. And this causes an increased frequency of collisions with the container. The increased frequency of collisions leads to increase of forces that are exerted on the walls of the container. Now, previously we used a piston that could move up and down, and we saw the volume increase as a result. Now, in this case, the volume cannot change because it's fixed in place. The only thing that can change is actually the pressure of the container. Now, as long as we have a container that can withstand the pressures that are exerted by the forces of the gas, everything is okay. But if the temperature increases too much, the pressures will eventually exceed the capabilities of this container to withstand an explosion. So let's summarize this. When the temperature of a gas increases, the pressure increases. And when the temperature of a gas decreases, the pressure decreases. Now, we can convert this understanding into symbolic notation and then derive Gay-Lussac's law from these observations. We see that pressure is directly proportional to temperature. So pressure is equal to some gas constant K times the temperature. Therefore, P divided by T, or pressure divided by temperature, is equal to a constant. So if the ratio of pressure to temperature is a constant, that means any ratio for that same gas of pressure to temperature is also a constant. So the initial ratio or the final ratio will be equal to the same thing. That means they're also equal to each other. So we can write down Gay-Lussac's law like this. P sub 1 divided by T sub 1 is equal to P sub 2 divided by T sub 2, where the subscripts here are just trying to indicate the before a change and after a change, or the initial and the final conditions for a gas. So this is Gay-Lussac's law in the form that we typically use. So we'll know, say, the initial pressure and the initial temperature, and maybe the final temperature, and from that we can derive the final pressure. So let's go to the next page. We have one more gas law to learn about. So here in the last part of today's lesson, we're going to talk about Avogadro's law. And Avogadro's law might be kind of the easiest one to understand, actually. What it does is it relates the volume of a gas to the number of molecules present. And when I say number of molecules, what I really am referring to is the moles, the number of moles present of that gas. So how do you think the volume of a gas would be affected if we increased the number of molecules present? So let's refer to the number of molecules present by the symbol N. This is actually moles of a gas, right? And that's the same as the number of molecules. Now, if we increased N, what would happen to the volume of a gas? Well, that's right, the volume would increase if the number of moles increases. Now, why is that? Well, by increasing the number of molecules or moles of a gas present, we are also increasing the number of collisions with the container. And by increasing the number of collisions with the container, we increase the pressure. And if the volume can change, it will increase as a result. So with that in mind, let's see if we can derive Avogadro's law from this observation. So we see that the moles of a gas and its volume are directly proportional to one another. So by increasing the moles, we increase the volume, or decreasing the moles also decreases the volume. We can write this out in an equation where N is equal to K times V, where that K is that constant again. And by a rearrangement, we can see that N sub 1, or the initial moles, divided by the initial volume is equal to that constant. We can also say that some other N divided by some other V, N2 and V2, is also equal to that constant, and therefore these two ratios are equal to one another. This is known as Avogadro's law. And Avogadro's law in this form actually leads us to a very useful conversion factor that we will use in some problems. It's called the molar volume of a gas. The molar volume of a gas is something that can be determined at standard temperature and pressure. Standard temperature and pressure is defined as 0 degrees Celsius and 1 atmosphere of pressure. That's 760 millimeters of mercury. And it turns out at STP, or at standard temperature and pressure, the volume of a gas, of 1 mole of a gas, is a known or a fixed quantity. And it turns out for any gas, 1 mole of a gas at STP has the same volume as any other gas. And it turns out to be 22.4 liters. So at STP, 1 mole of any gas has a volume of 22.4 liters. This turns out to be something very useful that we'll use as a conversion factor in certain problems that involve specifically standard temperature and pressure, because it saves a number of steps for us. We can go directly from volume into moles or from moles into volume using this conversion factor. So with that, I will end today's lesson. Please let me know if you have any questions, and I will see you soon. Take care.